Hey folks, so we are talking center of mass today. I introduce it during the momentum unit because that's where you will see it be applied the most in this course, but really it's kind of a concept that's been following us around for a while. So I have this eagle toy. It's made of plastic and it's got this shape to it, and I'll show it under the camera here. And it's a physics toy. And the reason why it's a physics toy is because if I put my finger under the beak, the bird balances on my fingertip. And it's something that might seem a little mysterious to you as to how the bird is doing that, and that concept has to do with center of mass. And so I'll introduce the concept and go back to the bird. The center of mass is defined as the average location of the mass in an object or system. So if we think about this object, the center of mass is the point at which you can balance something. And so the center of mass of this bird is right where the beak is, or the tip of the beak. So if I put the tip of the beak somewhere, the bird automatically balances on that point. And so, that's the average location of all the mass in this bird. So, the wings are made of they're put in a certain shape, so there's mass kind of all over the place, and the average location is the beak. If you think about the solar system, obviously we have planets that are moving, and so the planets and the sun and all the moons on all the planets form a big system of planets and moons and the star. And the center of mass of the solar system is inside the sun, but it moves around all the time because the planets are always in different locations as time passes. But the center of mass of the solar system is somewhere inside the sun at all times. Actually, I could be wrong about that. I'll just leave that in the video, and you can correct me if you do some research. But anyway, center of mass is a very important concept. It's basically every concept that we've studied in physics so far. It's really the center of mass that does the things that we've talked about. And so I'll talk about that kind of throughout, but let's focus on momentum first. The average location of the mass of an object, so x is our variable for position, and cm is our subscript for center of mass. So this is the position of the center of mass. And it's a weighted average method. So for a system that has two particles, it would be the mass of the first particle times the position of the first particle, plus the mass of the second particle times the position of the second particle, divided by the total mass of the system. Now, you don't need to know this equation. I'm just using it to kind of prove something about momentum. This could continue on for infinity. If we involved the solar system and all the moons, we'd have dozens of terms here. So this could just continue. So it's the product of mass and position. It's the sum of those products divided by the mass of the system. And so that's that's what you'd get. If you did that for this object, you would find that the position was here. So it's a two-dimensional thing. So you can involve the x and the y. You would find the average position in the x direction, the average position in the y direction, and that would basically tell you a coordinate in the realm of this bird where the center of mass is. Center of mass doesn't have to be inside an object, which is important for momentum. Now, because we're studying mechanics, we want to imagine this scenario. If the center of mass is moving, so we're transition here from position to displacement. So delta x is our variable for displacement, and so the displacement of the center of mass, right? If I take the bird and I move it over here, I have just displaced every single particle in the bird. And so the formula shifts a little bit. It's the mass of the first object times the displacement of the first object. And then that continues for the second object, and I divide by their total masses. And so, again, the center of mass can move if the entire object moves, or if one or more objects in a system moves, then there can be a displacement of the center of mass. Now, that displacement of the bird, right, it like took some amount of time. So now that I have an expression for the displacement of the center of mass, I will now show you the expression for velocity of the center of mass. And so what I do to get velocity is the rate of change in position. So I would take the displacement of the center of mass and I would divide it by a time interval. And this can be any time interval, but this is, we're just deriving it, so it's a variable. So the displacement of the center of mass divided by time, this would be the velocity of the center of mass. If I divide this entire expression by time, every term in the numerator would then be divided by time. And I would get the mass of the first one times its displacement divided by time. Displacement divided by time is velocity. And so I get the mass of the first particle times its velocity plus the mass of the second particle times its velocity. The numerator stays the same. So, there's kind of ways to work with fractions. I could have just put delta t down in the denominator, and it would be like the sum of all the masses times delta t. But I can also divide delta t into the numerator. And so I have to do that for every term. And so every displacement divided by time becomes a velocity. And so something very relevant happens in terms of momentum. The numerator of this fraction is momentums, or momenta. Mass times velocity plus mass times velocity. This represents the total momentum of the system. And so center of mass, if the center of mass is moving, and even if it's not, we can make a statement about momentum. We know that if this expression represents the total momentum of a system, if that system is a closed system, which is what we've been talking about, the total momentum of the system is constant. If this is constant, and obviously the mass is going to be constant, then this is constant. And so we arrive at this idea that the velocity of the center of mass of a system is constant in a closed system. Okay. And so that's really like a pretty important idea. And for those of you taking the AP exam, every single exam so far, and of course it will be broken this year, but I'll just say it anyway. Every single exam has had one question about this. That just, if you don't remember this concept, it seems like a totally bizarre question. But as long as you recognize that the center of mass of a system is constant, the velocity is in a closed system, then it's like a new way to apply conservation of momentum. And so, you can imagine that like we've talked about like explosions. And so if you have like a cart explosion where the two carts are up against one another, if they're not moving, their velocity of their center of mass is 0. When that explosion happens, what this expression says is even as they are moving apart, their center of mass, if it had an initial velocity of 0, it still has an initial velocity of 0. So the center of mass would like stay right here even as the carts moved away from one another. And so that's kind of powerful, that that velocity will stay the same during a conservation of momentum event. So explosions and then elastic and inelastic collisions, the velocity of the center of mass stays the same. Now, if the system is open, meaning if there's an external net force, the velocity of the center mass is going to change. And so, we can't apply this to every situation. We have to be able to recognize when there are kind of the right situations. Now, I said that Center of mass applies to everything. So maybe this is actually the most important part of the video that I saved for the 11th minute. But center of mass applies to everything. So if we think about projectile motions, and for whatever reason I was thinking about like a hockey fight, it's happened before, it'll happen again when one player of one team skates up to another player and pushes them and they just fall. Now, because their like skates are on ice, that's a low friction surface. So as the person, the person standing like this, as the person gets pushed, they move like this. They don't just kind of fall over. Their skates leave the ground and they kind of like, their feet like flip up in the air. So we've studied projectile motion, meaning if something like leaves the ground horizontally, it's going to take the shape of a parabola. Well, what center of mass says about this is that skater's center of mass will behave exactly like a projectile. It'll have like a beautiful parabolic shape. If you could identify their center of mass, somewhere in the middle of their torso, that center of mass will have that parabolic shape, but nothing else needs to. So their head would have kind of like a more extreme shape to it, like it would move horizontally and then it would just kind of like whip down. Their feet would have kind of the strangest shape, where the feet would go up first and then fall back down. So even though different parts of a person's body would have very erratic shapes to their motion, their center of mass would have that perfect parabola. So the center of mass is the part of something, or the location in space, that actually obeys everything that we've talked about. So kinematics, net force, and now momentum, and also circular motion. Circular motion is kind of interesting because you can have like a system of planets or a system of stars that orbit one another. Let's say it's two planets that orbit one another, and collectively they orbit a star. And I'll draw a picture because this is going to get pretty abstract otherwise. So here's a star, and you have a system of two planets. And I'll try and do service to this. Those two planets are going to orbit this star. Well, if they are orbiting one another, then the red planet is going to have this like curly Q shape to it, its orbit. The blue planet is going to have kind of like the inverse. I'm doing a bad job of this, but it's going to have kind of the reverse curly Q shape because they're going to travel around one another. So they have this super bizarre pattern of motion, but if you can identify their center of mass, the center of mass is going to have this perfectly circular or elliptical orbit, regardless of what the planets are doing at one time. So everything that we've talked about, we can make it more complex by adding more objects. The more objects we add, the more complex the individual behaviors are. But if we think in terms of center of mass, then everything behaves exactly as we've studied. And so that's kind of the final word on center of mass. We'll talk about it as we review for the exam. We'll kind of look at when and where center of mass shows up. And that's it.